There we go. I hope that you see my presentation now. Yes, so thank you very much for the introduction to it. I will be talking about remote sensing derived ice shelf basal melt rates. And in this presentation, I want to go through 4 different things. So first of all, how do we derive basal melt rates from remote sensing, both the challenges and the differences that we see between the different products. Then I want to highlight the importance of high spatial resolution. And then I will talk about some future possibilities from a remote sensing perspective, but also from more an intercomparison perspective. So let's first start off with deriving basal melt rates from remote sensing, challenges and differences. So here we have a sketch of an ice shelf, and indicated by the red arrow, we have some sort of warm water that can cause melting from below of the ice shelf, which then thins the ice shelf. And this thinning can be described by this equation here, which is just the mass conservation. And essentially what it just says is that any thickness change that we observe has to be described by the ice flux divergence. So that's stretching and compressing of the ice, and it's the surface mass balance and the basal mass balance. And if it's, of course, this latter component, the basal mass balance or the basal melt rate, which we are interested in. And it is this equation which all of the remote sensing products out there that we base our basal melt rates on. So what we have is actually, we assume that we don't assume, but if we know something about the thickness change, the ice flux divergence, and the surface mass balance, then we end up with a residual, which we assume to be the basal melt rate of the ice shelves. So if we look into the different components that we have here, then the surface mass balance, that is something which we all get from models. It can be different models that we get the surface mass balance from, but here we don't really see any difference in how that then impacts the basal melt rate, because the resolution of these models is rather coarse. So as long as we just choose this, as long as we don't switch in between models within the same product, then this is not where the difference in the different basal melt rate products out there is to be found. If we look at the ice flux divergence, then that's the stretching and the compression of the ice. Then what we do is that we use surface velocities, and then we assume that the surface velocity is actually the same as the average velocity down the ice column, and that's a fair assumption on ice shelves. Then how we numerically solve this ice flux divergence terms, that can differ a bit, and it can also have smaller impacts on the melt rates, especially when you work on high resolution. But again, this is also not where the biggest difference is found in between the different remote sensing products. Here in this part, we also have to make some assumptions about Föhn and hydrostatic equilibrium, and that I will get back to later. So where the difference is really found is in this thickness change part, and that's where we come in with our remote sensing products and the difference that we have. So if we go back to our ice shelf here, then from satellites, we can measure the surface elevation of the ice shelf. And when the ice shelf then thins due to one or the other reason, then we can measure this new surface elevation. So what we measure is the surface elevation change. And then the question is, how do we then get from a surface elevation change to a thickness change? Well, we first of all have to assume hydrostatic equilibrium. That is how we could basically get from a surface elevation change to a thickness change. And assuming hydrostatic equilibrium is not, well, that causes a lot of issues, especially in the grounding zone, because the ice does not just go from being grounded to floating perfectly in hydrostatic equilibrium. There are different ways that we go around this issue, with gradually adjusting from the grounding line until some distance away from the grounding line, or simply just cutting away the grounding zone. But it does not change the fact that, and this is a very important message that I want to get across, that you should not trust remote sensing products near the grounding zone. It is simple as that, because we cannot resolve it that well when we assume hydrostatic equilibrium. Another component, which is, in my point of view, the most annoying component in the cryosphere, that's the Föhn. So there are Föhn on these ice shelves, and when there's a thickness change, well, it can also be due to the fern air content that we see, and we have to take the fern into consideration one way or another. And usually we do that. We again get that from models, and the fern models, they are then also forced by, they also need data from models such as WACMO, MA, and those kind of other models. So they are also, of course, resolution. And that's what we have to work with. Some people assume that the fern air content is constant in time. Some assume that it's changing in time. But again, the models are actually not, I would have to say the models are actually not that great. So if we, whether we choose to assume that it's constant or changing in time does not impact our results that much. So it's not here that we find the difference in how the different remote sensing products they are, the basal mold rate products that we have, but that is really found in the surface elevation data that we use to derive the surface elevation change. So this is the main reason in differences in the remote sensing basal mold rate products. And I want to dig a bit deeper into that now when I want to talk about the importance of high spatial resolution. So here are some satellite images from Pine Island ice shelf, where indicated by the arrow in, let me just use a laser pointer, indicated by the arrow here, we see a channel here, or it says here we just see a surface depression, but it's a basal channel on the ice shelf. And then with time, it becomes more and more pronounced. And we actually start also see some carving events, and we can see how it really also cuts where we have this basal channel. So these basal channels, they are very important for the stability or the instability of ice shelves. And it's very important that we are able to capture these channels. And as you will see now, that requires high resolution. So here we see an example of some basal mold rates from the Dodson and Crossan ice shelf. It's a product by Adesumili et al., which I think that many of you might be familiar with. And this is a great product because it's the first, well, I would say first high resolution product of more or less all ice shelves in Antarctica. And what we do see is that we do see that that the basal molting is not the same all over the ice shelf. We see channels and we see other features. But a later study here by Davison et al., where here we can really see more detail into this melting pattern. And also here with my product Burgee, we can see even more spatial detail. And the reason for this, well, I said that it has to do with the surface elevation data that we use. And to show that, and here I have again the Burgee melt rates to the left and the Adesumili melt rates to the right. So in Adesumili, they make use of cryosat-2 measurements. And what I have shown here is that the melt rates, and then with the green dots on top is the cryosat-2 measurement points. And what you can see is that there's still a lot of area that is not seen by cryosat-2. And the reason for that is that cryosat-2 measures the point nearest to the satellite. And that then causes these different gaps that we see in the data, and also means that they do not measure. They measure a lot of different points, which are then averaged over a bigger region. For the Davison product that we also saw, they get a bit more information for every single cryosat-2 point, and they use something called swath processing, which it just means that they get more information out every single point, and that then increases the spatial detail a bit. But in Burgee, we make use of the reference elevation model of Antarctica, which has a 2-meter spatial resolution. So what we can see here is in the surface elevation data to the left, this is the kind of the quality of data that we use in Burgee, and to the right is the surface elevation derived from the cryosat-2 points. And we can see there's a big difference in how much detail we get over the ice shelves. And that is then also what then makes a difference in the melt products that we have. So also to give an example here on the Totten ice shelf, we have again Adesumili melt rates. We have the Davison melt rates and we have the Burgee melt rates. And what we can see here in Burgee is also some of these channels that were found in other products. They're much narrower and they're much more well defined. And we also see even more channels, and we do also see a lot of more mess towards the ice shelf front where it's highly crevassed. So it's not just, there are also downsides of going to a higher resolution. I have to admit that. But if we then look again into the cryostat 2 points that we see here and what that means for the surface elevation, then these channels that we have on the ice shelf that are clearly visible in the Rima mosaic, they are left completely unseen by cryostat 2. And that means that one of the key regions of the ice shelves cannot be fully captured by cryostat 2 alone. So we actually studied the impact of this high resolution on more or less all of the ice shelves in Antarctica that are subject to the highest melt rates. And what we did was that we focused on all of the different channels on the different ice shelves and looked at, okay, how long time will it take for these channels to break through? So here we have the time on the x-axis, and we have the ratio between the thickness in the channel and the thickness outside of a channel. So at 0, there is no channel, and at 1, the channel breaks through. The usual way to kind of estimate the breakthrough time of a channel would be this linear incision line where you say, okay, there's a peak melt rate within the channel of 10 meters per year, and the channel is 100 meters thick, then it takes 10 years for that channel to break through. But that is not the case, because we have to take secondary flow into consideration. And secondary flow is simply that the ice will flow towards the channel and trying to close up this channel. So channels, they can actually sustain, they don't have to break through, but that depends on the melt rate within the channel, because this is the case for a low melting scenario. If we increase the melt rate and if we increase it even more, then what we see is that channel breakthrough is actually possible. And the higher the melt rate is within the channel, the closer we get to the linear incision line. So what impact does this have when we take the peak melt rates from the different products within the channel? Well, first I wanted to say this can also be put into a phase space where we have the peak melt rate on the x-axis and the ice thickness on the y-axis. That's the ice thickness outside of the channel. And what we see here is the normalized breakthrough time, and that is the secondary flow breakthrough time normalized by the linear breakthrough time. So that means that if it's 1, then the secondary flow breakthrough time is the same as the linear breakthrough time. And when it gets more and more yellow, then it takes much longer time than the linear breakthrough time. And in some cases, they might not break through at all. What you will notice here is that higher peak melt rates in general lead to shorter breakthrough times. And below roughly 400 meters of ice thickness, there's almost no difference between the secondary flow breakthrough time and the linear breakthrough time. So if we now get the peak melt rates within channels of the different products that we have here, then what you will see is here we have the peak melt rate on the x-axis and the ice thickness on the y-axis. Then in red we have the Burgee, so that's our high resolution product. And those red dots are much further to the right than Davison in yellow and Addison-Milly in gray. And if we zoom in on this region here, then we see the same picture with red dots further to the right. Then we have the yellow and the gray dots. And if we then put the normalized breakthrough times behind it, then it's clear that, okay, higher peak melt rates within the channels, that also means that it's a shorter breakthrough time for these channels to break through. And the reason that we get these higher peak melt rates within the channel is because, compared to the other products that rely on cryostat 2 only, is because cryostat 2 cannot capture the channels properly. They cannot measure like the deepest points of the channels where we usually have some of the highest melt rates. So if we also look at the linear breakthrough time here, then we will now see that it's much faster for a channel to break through. So the red dots further to the left, and then the yellow and the gray dots. And zooming in on the region where we have the ice thicknesses below the 400 meters, so where the secondary flow and the linear breakthrough times are more or less the same. And we can again see that we have faster breakthrough for Burgee than for Davison and Addison-Milling. So we also looked a bit further to what this means, because of course, if you say that it takes so and so long for a channel to break through, then that only makes sense if it can actually break through before it reaches the ice shelf front. So the time that it takes for the ice to advect to the ice shelf front. And we looked at that here. So we have the colors of this is the Dodson Crossen and the Pine Island ice shelves, and we have the colors here indicating the residence time of the ice. And then the colors, then we have indicated here some of the channels, and the colors of the channel indicate also indicates the breakthrough time, or the Burgee breakthrough time. But if we, for instance, look at this front part here of the Dodson channel, then we will see that here the residence time is something around 50 to 100 years or so, but the Burgee breakthrough time is 33 years. For Davison, the peak melt rate was not high enough to even be able to cause any breakthrough at all, and for Addison-Milling, the breakthrough time here is 42 years. So this indicates that Burgee also means that with Burgee we're able to get these, or we get these shorter breakthrough times because we are able to catch the higher peak melt rates within the channels, and that has really has an impact on or how we assess the weakness of the ice shelves. And we see that even on Pine Island, there are channels that have the ability, like Pine Island, which is a fast-flowing ice shelf. Even there, the channels can actually break through before they reach the ice shelf front. So moving from there, where I hope that it's now clear that high spatial resolution is needed, then I want to dive a bit more into the future possibilities from a remote sensing perspective, and how we can improve our remote sensing derived basal melt rates, because they are not perfect. Well, one thing which I think would be very interesting would be to do a data fusion approach to achieve both high spatial temporal resolution surface elevations, which would then lead to higher resolution basal melt rates. So right now we can get high spatial resolution basal melt rates, and I know that at the British Antarctic Survey, there's a PhD candidate there working on getting much higher temporal resolution basal melt rates from Chrysler 2. And if we could combine those two data sets in some or the other way, that would be really beneficial, I think. Another thing is better implementation of hydrostatic equilibrium or lack thereof near grounding zones and pinning points. And for that, I think we really need help from the modeling community on how we can. Because it still has to be simple to be able to do this. And yeah, for this, yeah, the correction that we need to apply still has to be rather simple, but we can certainly do it better than what we're doing right now. Then if we move into the future possibilities from an intercomparison perspective, then I here have a figure showing the spatial and temporal grid size or resolution of the different basal melting products out there. So these are from a satellite perspective or the remote sensing perspective. But if we also add some of the field measurements that we have here, then from satellites we can get, you will notice that all of the satellite products here, they have quite good ice shelf wide coverage. They have a more darker red color. That means that we can cover great areas. But from something such as an AP rest or ocean moorings, we can get basal melt rates at a very high temporal resolution, daily, hourly. And from UAVs such as IceFin, we can get basal melt rates at a sub-meter spatial scale, but of course, from a UAV, or if you put ice fin under an ice shelf, then it's a snapshot in time. And the same is with the APRS and moorings. It's a point measurement. So what I think would be really needed is something down the lines as what have been done here, where they have compared the Addis-Milli melt rates with measurements from with melt rates from moorings and APRS measurements, but to even broaden that network even more and make a joint and structured campaign of all measurements and modeling techniques that are out there for basal melting in, I just called it here, BAMIP basal melting intercomparison project, but where we really make sure that we connect all of these different methods that there are for assessing basal melt rates and put up a structured network. And it, of course, has to be over a time period which is long enough for the satellite measurements to also, or for the satellite techniques to also generate melt rates. But we also need to be able to then compare in between the different points of APRS, for instance, with ice fin or something like that. And I know that this is a very expensive exercise, but I think that it would really have a huge impact on our understanding of basal melt rate and really help validating all of these different techniques that we have. So take-home messages. Remote sensing derived basal melt rates mainly depend on the choice of surface elevation data, and do not trust our results near the grounding zone. Do not trust the melt rates. You can trust the pattern, but don't trust the magnitude of the melt rates near the grounding zone. High resolution is needed to fully capture these basal channels, and they are important to assess correctly assess the stability of an ice shelf. And in terms of improvement of our remote sensing product, I think data fusion, so high spatial temporal resolution, is really needed, and also better implementation of hydrostatic equilibrium, or lack thereof, near the grounding zone. And to improve our understanding of basal melting in general and also cross-validate our different products, I think that we need a bigger campaign where we make sure to add all of these products in the same time. And with that, I would like to say thank you.
Thanks very much, Anne-Sophie. We have time for a few questions, so please do feel free if anyone has any questions to unmute. And Roland, go ahead.
Thanks very much, Anne-Sophie. I had two questions. I was a little puzzled about your discussion of melt rate and breakthrough. Whether this is simply a difference of terminology about the partial time derivative of ice thickness versus some different interpretation, but there will be very high melt rates even when an ice shelf is in dynamic equilibrium. So I'm a little confused about that. The second question I had was, in a situation where you've got as the ice shelf flows, you've got the thickness evolving dynamically, and as a result of the melting, does it become dangerous to assume that hydrostatic equilibrium applies over narrow basal channels, and might there in fact be bridging stresses in those areas?
Yeah, so for the hydrostatic equilibrium, I think that the area of the most concern is the grounding zone, but for sure there are bridging stresses acting across basal channels, which will also impact, or which will also ensure that the ice shelf is not floating perfectly in hydrostatic equilibrium. I do, however, think that it's the grounding zone right now which is the more important part of it. But if there was a solution to both problems at the same time, that would be nice. Your first question was something with the breakthrough times. I don't remember exactly what it was, but
well, you have a very high melt rate.
Yeah.
You have a very high melt rate under an ice shelf that's in fact in equilibrium, because of the fact that the ice flux divergence is compensating the melt rate.
Yeah, so that's a case that you can have, but you can also have a case where the melt rate is so high that it can cause breakthrough. Or well, I should change the words, because it cannot cause breakthrough, but what we believe can happen, which has also been seen on Pine Island, is that at some point the ice there will become so thin that it can cause fracturing, and in that sense weakening of the ice shelf. So it's not actual breakthrough of the channel, but the channel will become so thin that it can then cause fracturing, and fracturing that which can cause ice shelf retreat and that kind of stuff. I hope that answers the question.
Yeah, I just feel that that's a matter of thickness change, not purely a matter of the melt rate. In that a large fraction of the melt rate might be involved in simply maintaining the shelf, the thickness gradient in a steady ice shelf.
Yeah, so for that, well, that part, the modeling part with the different normalized breakthrough times, that was made from Martin, that's from Martin Weering, so a colleague of mine. So I'm not sure exactly how, but it's from model results that we have this relationship of that we have the normalized breakthrough time, and they are also related to both the width of the channels and also the thickness of the channels and also the ice around it. So I'm not sure that I can answer that. He would be the one to answer that question, really.
If I may jump in, I will talk about this in my next talk.
Excellent. we might move on and hear from Yoshi and then Sue, and then I think we'll have to end the questions there. But Yoshi, go ahead.
Hi, Anne-Sophie. I think my question was pretty much related to the breakthrough time, so I'll wait until the end of the session to ask questions if I still have some questions. It was a great talk.
Thank you.
Thanks. Hopefully this should be a quick one. I wondered when I looked at your comparison of the Burgee and the Addison-Millie data products, have you tried smoothing the Burgee product and seeing if it ends up looking like the Addison-Millie product?
So we have also, yes, we have.
Yep.
So we have also generated Burgee at different grid sizes and also the same grid size as Addison-Millie. So the overall pattern is the same, but it's really that because Cryo-2 cannot capture the deep surface depression, so where we have the channels, then the melt rate in the channel will still be underestimated by Addison-Millie, but the overall melt patterns, they are more or less the same. Yeah, and that's good. That's good.
Yeah, that's great news.
Yeah.
Thank you.
Yeah.
Right, please, everyone join me again in thanking Anne-Sophie for a really excellent talk. And we're now going to move on to the second part of our session, and we'll be hearing from Dr. Ole Zeising. Ole studied geophysics at the University of Hamburg in Germany, and his PhD in glaciology jointly between RV and the University of Bremen was looking at phase-sensitive radar to determine basal melt rates. But Ole's current role is focusing on ice-ocean interactions and ice dynamics using both radar and seismic. So it's a pleasure to have you speak. Thanks, Ole.
Thank you very much for the nice introduction. Yeah, while Anne-Sophie talked about the melt rate estimate over larger areas, I want to focus on smaller areas and to focus on more details. And I will do this at the example of two studies that we did in Greenland and Antarctica. And I will also highlight the limitations and the challenges we face by using ground-based radar systems. I want to start with a bit of background about how to measure basal melting. And already Anne-Sophie did a great introduction into this, so I can do this a bit quicker here. So basal melting is changing the ice thickness. And we can measure the ice thickness with different geophysical measurements. But the problem is that there are the other processes that also change the ice thickness, like snow accumulation and ablation, firn densification, and vertical strain, so from the ice deformation, and of course, at the ice base, melting. And while the estimation from satellite-based measurements also requires different products about accumulation and densification processes, we can use ground-based radar systems to measure all of these processes, or how these influence the ice thickness. So that's a big advantage, and this is why ground-based radar measurements allow to measure melt rates in a higher resolution. The mostly used radar to measure basal melting is the autonomous phase-sensitive radio sounder, better known as the APIRS system. It is a radar system developed at the British Antarctic Survey, and it was designed to measure basal melting. And the APIRS itself is just the small yellow pilly case you see here in the image. And with battery and 2 antennas, it's a very lightweight and portable radar system that allows to measure, to do measurement in just a few minutes. But as Anne-Sophie showed, it's a point measurement. You cannot, so far, not really, drive around, although people work on this. But the system requires a repeat measurement. So, for example, after a year, you go back to the same surface location. So we have to mark it with bamboos, for example. And based on these two measurements, the basal melt rate, or vertical displacements in general in the ice and at the ice base, can be measured in very high resolution, so an accuracy of about 1 millimeter. And next, I want to show you how this can be done on an example from an Antarctic ice shelf. So here you see the amplitude profile from a measurement taken end of December 2018. And you can see that the amplitudes decrease with depth until a depth of roughly 325 meters, when the amplitude increase rapidly. And this is the reflection at the ice base, because the ice-ocean interface is a very bright reflector. And this measurement was repeated like 11 months later, and the profile looks basically the same. In the ice, we have the same amplitudes scattered. And then at the ice base, and this is what you can see on the left in a zoomed in section of the ice base, we also see this same amplitude there, but it has shifted. It has shifted towards the surface. And with PRS and by analyzing the phase and also amplitude, we can estimate this shift very precisely. And in this example, this shows us that the ice has thinned by 45 centimeters in between the two measurements. So now we know how the ice thickness has changed. But as I said before, there are the different processes that cause this change. And we need to measure the contribution from all of them to get the only unknown, the basal melt rate. So what we can do is we analyze vertical displacements in the ice exactly in the same way as we do with the ice base. And that's how it looks like. So when we look at the very last of these gray dots and think how this change has been occurred. So it shows us that at the depth of 300 meters, the ice has thinned by a few centimeters. And this thinning is the sum of everything that happens above, so between the surface and that depth. That is so snow accumulation, firn densification, and the vertical strain. And everything that happens below this point is just the strain within the last 25 meters and the basal melting. So the only thing we need to do is to know the strain rate and to extrapolate it to the ice base. And we do this by analyzing all the displacements below the firn ice transition, so to avoid firn compaction. And then we can extrapolate this. And this vertical displacement is really the sum of all the contributions that we can estimate. And then the only unknown is the basal melting. And that's why we can measure all the different parts here with just two measurements with the ground-based radar system. And now I want to start with the first study of the extreme ice shelf, which is a cold cavity ice shelf in East Antarctica and Dronning Maudland. Here, since 2018-19, we did a yearly repeat of an APIRS measurement at different locations. So once a year, we went to this location, we set up the APIRS and the antennas with the battery and did a measurement for a few minutes, and then we went to the next location. And we did this to analyze the spatial melt rate variation. And what we find is that near Neumeier station, we observed higher melt rates of 2 meters and above, and they have increased in time. Then we have this cluster here in the center of 5, 6, 7 stations. So the number has grown since we started. And here we observed lower melt rates of roughly about 40 centimeters per year. And on the figure on the left, you see the different melt rates in between 2 visits. And you can see at some locations, we see a slight increase, but in overall, there's a variability, but it's not a clear signal that all of them show an increasing melt rate or so. But it's very challenging to interpret these melt rates because they have measured not exactly after a year, but somewhere in the summer season. So the green dot in all of these panels show the first measurement that was the first period between December 2018 and November 2019. So there were just 11 months in between. And actually, the example I showed you before was this period here at extreme ice shelf. But the second year, we repeated the measurement in January 2021. So there were like 13 months in between. And so 1.5 summer seasons. So in case we have a seasonal melt rate here, that means, as for example, observed at other ice shelves in Dronning Maudland, an increase in summer, this would affect our melt rate. So we measure melting, but by calculating the rate, we assume that the melting is constant over time. But this analysis of the spatial melt rate variability by doing measurements once a year does not tell us how the seasonality is in melting. And that brings me to the first key message I have, that melt rates from yearly repeated measurements must be interpreted with caution when the seasonality is unknown. So how do we know the seasonality? And that's the main advantage of this radar system, because it does not only allow us to do these yearly repeated measurements, it allows us to operate it autonomously. So with a big battery, we can bury it beneath the surface, and it can measure for example, a whole year or several years actually. And during these years, it can measure like once an hour. That's how we operated at extreme ice shelf. And I want to show you now the first of 4 years of measurements that we have done at extreme ice shelf. And first, so it started in April 2020, and until July, we observed low melt rates of below 0.5 meters per year. But then in August, a melt event occurred, and melt rates increased to 1 meter per year. This melt event lasted for 2 weeks, and right after that, there was an even stronger melt event that lasted for a month. And in this melt event, melt rates increased to 1.8 meters per year. So roughly 5 times higher than the melt rates we observed before. After this melt event, a third one occurred, but in general, in spring, the melt rates were much higher than in autumn and also than in summer, because in the end of November, melt rates decreased and stayed low through the whole summer. And this is exactly the opposite that was observed at other ice shelves in Dronning Maudland, for example, Nivelles-Isen or Mont-Baudin. But this definitely depends on the location where these measurements have been done. So in our study, now we found enhanced melting in winter and spring at extreme ice shelf. But we can also look at this in a different perspective and saying we found reduced melt rates in summer and autumn. But how can we explain this? Together with Tore Hattemann, we investigated this further by using plume simulations. And here I want to show you our hypothesis we have to explain high melt rates in winter at this location. So here you see the geometry of the extreme ice shelf and the Epirus location. And so the hypothesis that we have currently is that in summer, surface water that's pushed by winds beneath the extreme ice shelf, similar process that has been observed at many other ice shelves. And this surface water is less dense than the eastern shelf water that fills the cavity. And due to the lower density contrast to the ice shelf water plume, it has less buoyancy, and so it reduces the plume velocity. And that's why we observed reduced melt rates in summer based on this hypothesis. In winter, when there's the sea ice formation, dense eastern shelf water is produced. And this dense water erodes the stratification in the cavity. And so it causes an increase in the density. And by that, it enhances the flow velocity of the plume. And with that, the melt rates. So if this hypothesis is true, the basal melt rates at the extreme ice shelf is primarily affected by the plume velocity, while the temperature of the ambient water is only secondary. And if you want to know more details, this is part of the manuscript that's currently in review at the cryosphere, and it's a preprint, so you can access this via this QR code. Now I would like to do a jump from the southern to the northern hemisphere and want to go to the 79 North Glacier in northeast Greenland, which has a warm cavity ice shelf. So we are here in the northeastern part of Greenland, and this floating tongue of the 79 North Glacier is quite large for Greenland. It's 85 kilometers long and 20 kilometers wide. And here, there was a study 7 years ago from Ned Wilson et al. That did satellite remote sensing estimate of the basal melt rate. And they found rather low melt rates over most of the ice tongue, but closer to the grounding line, where the ice is more or less still freely floating, they observed higher melt rates of 50 to 60 meters per year. And we did an extensive study there in 2017 and 18. And since then, we operate autonomous phase-sensitive radar systems there. And we focus this in the area between downstream of the grounding line, where satellite measurements cannot measure melt rates. Because it's an ablation zone, it's not that easy to install an Epirus there. So we had to place it on the surface and more or less water sealed box. And with ablation, it goes down basically along to several bamboos to keep it in place, which worked more or less as planned. And here I would like to go into more details on how such a radargram looks like. We started this analysis in August 2016, and we observed an ice thickness of 400 meters. But within just a few months, the ice thickness decreased rapidly at a rate of roughly 100 meters per year for several months, until spring 2017, and then the thinning reduced. And they stayed low, so melt rates stayed low until the end of the measurement interval until July 2018. But what happened in spring 2017 when the thinning of the ice has changed, and so more or less the basal melt rate? One possibility is there's a temporal change. There's colder water flowing into the cavity. But there can be another explanation, meaning that with the reduced ice thickness or with increasing distance from the grounding line, the ice lost the contact to the warm water, which is in this cavity deep water. So we have the warm water below colder water on top. And based on this measurement, we cannot say if this was a temporal or a spatial reason. And that brings me to the second key message, that A-Pyrrhus measurements are Lagrangian measurements. And that means that we have a superposition of temporal and spatial variation. And based on one of these measurements, we can never distinguish between both. We cannot say this is temporal or this is a spatial effect. And to go a bit deeper into this, I want to talk about Lagrangian versus Eulerian perspective of melting. This is a very simple sketch of an ice sheet, an ice shelf. And now we say we operate an A-Pyrrhus near the grounding line, and the A-Pyrrhus moves with the ice and increases the distance to the grounding line. And in the figure on the bottom, you see how such a melt rate we observe along this line would look like, or along the whole floating part. And we assume that the ice is in a steady state. So at any point in time, we observe the same ice thickness. And this already shows that it's possible to measure high melt rates, but still the ice is in a steady state. And the important question is, how can we know that the high melt rate that we measured is able to keep the same ice thickness, or if this is above a certain threshold and it thins the ice? So in our example here, the Eulerian melt rate basically would be 0, as the ice thickness is not changing. And we can only measure this by bringing the A-Pyrrhus, or whatever we use, back to the first location and measure it again at the same coordinate. And if the ice is not in steady state, then we would measure a thinning or a thickening. And if we do a repeat of this measurement, then we would observe higher melt rates in a non-steady state. But that's very difficult when we zoom, let's say, in a steady state, we measured 100 meter per year melting, and in a non-steady state, 105 meters per year. How do we know that if we just do one measurement? And we really need to do a repeat measurement. We need to analyze how has the ice thickness changed and how do melt rates change over time. But when we do just one, we can never separate between temporal and spatial changes. So we have to do a repeat. And that's also a message that the Eulerian perspective, we need the Eulerian perspective from a repeat of Lagrangian measurements. And this is what we have done at the 17A North Glacier to further elaborate how the system changes over time and not by moving ice from the grounding line away. So this is the image I showed you before. And in July 2018, we put the A-Pyrrhus back to the same coordinate as 2 years before. And what we observed was really surprising, because the ice thickness has decreased by 50 meters in the 2 years. So we observed an Eulerian thinning, showing that this piece of ice that we observed in July 2018 at the coordinate where we started everything has experienced more thinning than the ice at the same spot 2 years before. So it shows that there were higher melt rates in between, and these melt rates are higher than to keep the same ice thickness. But, and that's the second very surprising thing, during the second time we measured at this location, the ice has barely changed its thickness. So we observed very low melt rates that were at the same location, like a magnitude lower than 2 years before. So at the end, in January 2020, when we had failure of the Epirus, the ice was 10 meters thicker than at the same spot 1.5, 2 years before. And this shows us how the system changes very quickly from high melt rates and so Eulerian thinning to reduce melt rates due to colder water. And this is what we interpreted here, that the decrease in Lagrangian basal melting since 2017-18 indicates an inflow of colder water into the cavity below the 79 North Glacier. And recently, this was confirmed by ocean observations published in Science just a few weeks ago. And if you're interested in more details, this is a paper we published early this year in the cryosphere. So to wrap up, I'll show you my key messages again and the recommendations I have. So the first key message was that melt rates from really repeated measurements must be interpreted with caution when the seasonality is unknown. So when you do a spatial analysis of the spatial distribution of melt rates, do this in combination with the temporal variability, because otherwise it's very hard to interpret the melt rates or the melting you observed. And the second key message, that Epirus measurements are always Lagrangian measurements. So there is superposition of temporal and spatial variation. This might not matter if you're at a location where the spatial variation along a flow line is low. For example, at Ekstrom ice shelf, we don't expect to have the spatial variation within a few kilometers. But when you do measurements near a grounding line where melt rates change quickly in the flow line direction, I really recommend doing repeat measurements, as you really need those to investigate what's going on and how the interannual variability looks like. So to have a long-term observation, you really have to go back to the same location all the time and remeasure what you have done. And that's it. And thank you very much for your attention.
Yes, thank you very much, Oli. This was a great presentation, and I already see a few hands raised. I think Felicity was first out, so no, Felicity is taking her hand down. Okay, suddenly a lot of hands popping down, right?
There's a question in the chat there if you want to look
Yeah,
at her.
there's I'm coming to that. There are questions in the chat as well. Yes, no, I just thank you for this great talk, and I think just an overarching comment, these two talks are complementing each other very nicely for the discussions that we're about to have, I guess. But let's limit questions to Ole's talk now in the first round. I just read from the chat. The first question is from I try to pronounce, I hope I do this roughly right, Ringpu Xiao.
And it's not a question, it's more like a comment. And sorry, I just take a shower, I'm at home. Forget about time difference. And I just turned on a 1D modeling recently, and I got in touch with the model developer, and they are very interested in my work. But anyway, my model result shows something agrees. My model result shows some agreement with what you said here, which is the velocity of the plume matters most when compared with the temperature of the ambient open ocean. Yeah. So I didn't know that you have a publication on the EGU. I will have a look, and maybe I will write some comments there or something, just to let you know the model result agrees with what you said. Yeah, good talk.
Okay.
Thank you.
Thank you very much. That's great to know.
Yeah.
Right. Thanks for your comment. Let's move on. Torgo also commented in the chat. Do you want to repeat that? Read out loud what you think. It was about that from an ice geometry perspective,
Yeah,
the
sure.
Lagrangian versus Yeah, maybe you go ahead.
Sorry. Yeah. Thanks for to both speakers. Great presentations. I learned a lot. To Olaf, I appreciate your explanation of the Lagrangian versus Eulerian observation or measurement of the ice thickness. just wanted to point out in your case of the steady state, your Eulerian melt rates are 0. But I assume, in fact, the ice sheet or ice shelf is still melting at the grounding line. It's only balanced by the grounding line flux, that there's no net thinning at that point. And from an ocean perspective, however, that melt rate would matter because it's a freshwater input or it's a water mass transformation that's still happening, although there is no net Eulerian perspective thinning of the ice shelf, right?
Of course, so we have Lagrangian melting all the time, but it's just the question if this Lagrangian melt rate is high enough or low enough to keep the ice thickness constant at the one coordinate. So from the Eulerian perspective, but of course melting is going on always, yeah.
Yeah, I think that stresses the point that one needs to be careful with the reporting or with the use of the data. And exactly know what kind of melt rates one looks at, right?
Yeah, that's very important. Yeah.
Thank you.
For now, I see no more hands raised. People may also speak if they feel enlightened. If not, yeah, Roland is having his hand up. Okay, go ahead.
Didn't want to be monopolizing the conversation. This last point that Toj just mentioned, that's what I was trying to raise in my question to and Sophie as well, that there is melting, there's just not thinning of the ice shelf. And the concept of Lagrangian melting is, since I assume you're still extracting the strain thinning of the ice shelf, the Lagrangian melting is the melting that was experienced by that column of ice as it traversed that region. And so for that particular epoch, that would actually be the average melt rate over that region. So I think this matter of was the ice shelf changing or not, and was there melting or not, one needs to keep a careful focus. I think that George's comment captured that pretty well.
Yes, I think that was a very useful comment, and I think the illustration of Ole was is as well applicable for the satellite perspective. I mean, there are even studies that show the difference if you interpret your satellite data in an Eulerian or Lagrangian framework. So this is certainly something to be aware of when dealing with these data sets. If nobody has any more specific questions to Ole, and I pause here to see if anybody is raising a hand, I'd like to make one overarching comment, and then I think we go on with the breakout groups. Again, this was a very nice combination of the point-wise measurements and the broad perspective measurements. I think, and we already discussed a few important aspects. I think one aspect that has not gotten much focus here yet is the most relevant for interpretation of satellite data, but maybe helped with by ground observations is what's happening at the ice surface. Surface mass balance was mentioned, and also it was mentioned that surface mass balance models are usually producing smooth fields, but there's much more that the satellites need to take care of when we try to estimate the height of the ice surface, and that's radar penetration depth of satellites, which may vary seasonally. That's tidal variations that come into play when you want to look at time variability or even may alias your observation, and all these things. I think there is a big Pandora's box that is not really opened and solved in interpreting that, but that's only my personal opinion. So as a primer for discussions, maybe. So let's move on. I hope Sue can help us where about